Hello and welcome to the Unit 3 podcast on section 9.1. So now we're going to segue into covalent bonding. I'm Mr. Sakaguchi.
And I am Mr. Lin.
And nothing's changed about that, so let us get into it. So we talked about electron loss and gain, but sometimes there isn't enough of a difference in electronegativity to have an actual electron transfer. Now, noble gases don't bond because they're already stable. Ionic compounds seek to stabilize themselves by transferring electrons.
Covalent compounds, on the other hand, which we're going to cover in more detail now, arises from sharing of electrons.
And this is their way of achieving stability and mimicking a noble gas-like configuration. So what is a covalent bond? Again, as Mr. Lin said before, that we're sharing valence electrons here.
So this happens usually with just nonmetals, okay? And when they share those electrons, that's what the covalent bond is. And as a result of that sharing, all the elements in that compound wind up possessing the correct number of electrons that they need for that noble gas config.
And you know, as formula units are to ionic compounds, molecules are to covalent compounds. Molecule kind of gets thrown a lot around things that don't necessarily apply. It applies to. So think of molecules as the smallest unit for covalent compounds, formula unit for ionic compounds. So the actual formation of a covalent bond, what ends up happening here is we're achieving an octet, and basically there are two forces that acts upon covalent bonds. There's the attractive force of the nuclei from different bonding atoms coming together,
and there's the repulsive force where the electrons and the protons between the atoms push away from each other.
So to look at this example a little bit on the right, this area here represents the shared pair of electrons, and the reason why they're not too close together is because there's repulsive forces pushing them away. You might also see this in terms of Lewis notation. So they're all electrons. The X's and the dots indicate just who has which electrons belong to which element. And whenever we have dots or electrons in between two symbols, that implies that they're being shared by both. So for instance, if I was going to count the octet of electrons for the fluorine on the left, it's 1, 2, 3, 4, 5, 6, 7, 8, ending with that red dot.
And it's the same on the other fluorine as well.
Right, so again, so notice that the red dots in the middle count for both elements. One other thing to be aware of is that there are some elements that do not exist in monatomic form. They are diatomic. In other words, they're always found in nature in their purest form, bonded to themselves. And they're represented here: HOF, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine.
Or I just refer to them as just Hofbrinkels.
Yeah, so if you ignore the twos, it's Hofbrinkel.
Right. So I say, remember your Hofbrinkels or your Brinkle gets Hoffed.
What?
Never mind.
Okay, let's move on. There are a few different kinds of covalent bonds to be aware of. The most common one, and the one we will always start with, are single covalent bonds. This is when one pair of electrons are being shared between two different elements.
The shared electrons are called the shared pair.
Yeah, they'll be referred to bonding pair, shared pair. They'll throw in a lot of terminology here that basically mean the same thing. There's a way to kind of look at how many single bonds certain nonmetals can form depending upon what group they're in. So for instance, 7A nonmetals and H can only form single bonds, and this is because they're all one electron short of achieving a noble gas configuration, so they don't form other kinds of bonds. 6A nonmetals can form up to 2 single bonds. 5A nonmetals can form 3, and 4A nonmetals can form 4 single bonds.
Also keep in mind that for every single every single covalent bond, there are a pair of electrons. So in our example here with the single bond between the two hydrogen atoms, there are 2 electrons. Okay, so if there is a question asking about how many electrons are in this molecule with this many bonds, just multiply by 2.
The other thing in terms of notation is this is acceptable to indicate a single bond. You'll also see dashes. A dash basically means two dots. Okay, and we only use those for bonding electrons. We usually don't use them for non-bonding electrons or electrons that are not involved in a covalent bond.
Right.
Another way to look at single bonds is to call them sigma bonds. And the idea of sigma bonds comes from the idea of our atomic orbitals. So if you go back to our atomic orbital stuff, if each element has atomic orbitals, in order to form a covalent bond, that means that these electron clouds or orbitals need to overlap. And when this overlapping takes place between either an S and an S and a P, or a P and a P sublevel, then we have the formation of a sigma bond. So don't worry about the hybridization stuff yet. We'll talk more about that later.
But keep in mind that for every single or for any type of covalent bond, there will be one sigma bond involved.
So this represents the S, and this is the P's for the carbon, and the overlap represents the sigma bond itself.
So in this structure where you got one carbon and 4 hydrogens and they're all bonded together, there's 4 single bonds. That means there's 4 sigma bonds in this.
And then notice the molecule on the bottom with the dashes.
Right.
We can also have double and triple bonds if necessary. A double bond is simply when 2 pairs of electrons are shared. Triple bonds are when 3 pairs are shared.
So showing up with the 6A elements, you get a double bond, and then with the 5A, where you can have up to 3 bonds, you can have a double and a single bond, or a single triple bond. A little confusing.
Or one triple bond.
Or one triple bond.
Otherwise it sounds weird. For 4A nonmetals, you can have 2 double bonds, and you can have a double or 2 singles, or a triple and a single. And again,
we're not talking baseball.
It could be. And the idea here is represented here. We can use 2 dashes to represent the double bond, or 4 electrons. These electrons that are not part of this are what we call non-bonding pairs, or non-bonding electrons. And then for nitrogen, we have a triple bond, which is 3 pairs.
Right. So when you have bonds that are more than singles, so we're talking about double and triple bonds, you wind up with something called a pi bond. And what these are, the way to describe these is they are bonds that are parallel to the sigma bond that's there. So let me break that down again. Whenever you have a multi-bond between 2 elements, you'll always have a sigma. And then everything after that, if you still have bonds going on between those same 2 elements, you'll have pi bonds. So sigma will always be there. There will always be one sigma. After that, the additional bonds following that would be pi. So a double would be formed of a sigma and a pi, and a triple bond will be a sigma followed with 2 pi bonds. You could say that there will always be sigma, and then if there's room left over, you have pi.
So with pi bonds take into account the spatial considerations for orbital overlap. So you have to remember, if I'm forming a double bond, those are 2 orbitals overlapping, right? So if I already have a sigma bond in place, like this, this area, this volume is already occupied, right, by the sigma bond. So if I want another pair of electrons to come into contact, this area is occupied. And because of rules, we can't have more than 2 electrons in this area. So what ends up happening is it gets the pi bond, even though this looks like a triple bond, is actually split. It's actually half a bond above and half of a pi bond below. And that's how the pi bond forms for a double bond. So it looks like a triple bond when I do this, but it's actually a sigma and half of a pi bond above and below. In this figure here, this kind of illustrates what's going on during a triple bond. So we have our sigma bond here, we have half of a pi bond here, the other half is down here, and then the third bond in the triple bond, which is the second pi bond, is half of it's coming out towards us, and the other half is behind the page. And so it kind of looks like this. So these are different representations of this molecule here.
And you're not going to run into any situations where you wind up with a quadruple bond. Those don't occur, so don't worry.
And you can see spatially why that would be, because all of the volume between the 2 atoms, between the 2 nuclei, are occupied already.
And it'd be almost impossible, pretty much, for an electron to fly off of the far end with the other far end to
The other thing to
connect.
keep in mind is that sigma bonds are stronger than pi bonds, and the fact that you have to cut the pi bonds in half to make them kind of makes, hopefully that makes a lot of sense. In terms of strength of covalent bonds, we can actually measure how strong a covalent bond is, or the amount of energy that we would get if we broke the bond. Very similar to like lattice energy for ionic bonds. But there are a lot of considerations, just like for lattice energy. For covalent bonds, the distance of the bonded nuclei matter. If the bond length is short, the bond is much stronger. Energy is released when a bond forms, just like with lattice, and so there's energy required to break a bond as well. The greater the bond associated energy, the closer the atoms are together. And then we've talked about endo and exothermic before. Remember, in endothermic reactions, energies has to be put into the process.
Right. So for that to happen, more energy has to be put into breaking the bond than what's released. And then oppositely, the exothermic means that more energy is released than the amount of energy that goes into breaking it in the first place.
So this kind of illustrates bond energy. This represents the bond length related to the bond energy itself. So notice, like, if there's no bond energy, if the two bonding atoms are too far apart, and as they get closer and closer together, the energy becomes greater. If the nuclei get too close together, the repulsive forces prevent the bond from forming, and this optimal trough represents the actual bond energy as a function of length.
Yep.
And I believe that's it. So until next time.